Hi everyone, welcome back to another Bandwidth Audio video here at HQ on our bench. Wanted to talk about something a little bit different today. I know a lot of our recent videos have been on Project 2845 progress. I guess with a quick aside, Project 2845 is pretty much done. We're just finishing up the last pieces relative to productization and getting it ready for um, customer deposits and orders and starting maybe some builds for those who are interested in it. I'll overlay a photo over this video showing the amplifier um, kind of on our bench getting wired up. I will say 2845 really beat all of our expectations by a long way. The thing performs totally awesome. Our transformers are amazing. The power supply is rock solid. We get, we get nearly full power down to 20 hertz on the thing and 35 kilohertz of bandwidth completely open loop with great noise performance and low THD. It's really, really an exceptional product and really blows the doors off of any of the other 845 based single-ended amplifiers I've seen on the market. So I'm really excited about that, and I'll do a full video on that product hopefully in a couple weeks, just once we finish up a few more things on it, and I'll have that on the bench and maybe we can run through some performance real time, which would be pretty fun. But back to the bench, related to Product 2845 or Project 2845, we've been seeing a lot of tube issues recently, actually both with some 845 tubes arcing, as well as, rectifier tubes arcing in that amplifier. And actually not just that amplifier, our other amplifiers, we've been seeing some rectifier tube arcs. And so it was kind of time to build our own high voltage custom vacuum tube rectifier. So this thing can test any of the, 8-pin octal audio, common audio rectifier tubes, or even non-common. This thing can test them and screen them prior to putting into an amplifier for issues with shorts. So a little bit of quick background info, and I don't want to belabor this too much, but commonly tube rectifiers used in a full wave rectifier arrangement where you've got a transformer that has a winding with a center tap. And so typically to get, say, like 400 volts RMS, so 400 volts times square root of 2 peak, held on this capacitor here for a DC voltage, you need a transformer that's 400 volts from one side to the center tap, and then another 400 volts from the center tap to the lower winding. So typically called like a 400-0-400 secondary power transformer. That's typically how those are rated. The peak inverse voltage on a full wave rectifier like that is actually really high because whenever, say this top leg of the transformer is conducting our tube rectifier is hot, it's on, and it's conducting out to the filter capacitor. As I said, this capacitor will hold the peak of that 400 volts. So that peak voltage would be 400 volts RMS, if that's what our transformer winding is at. 400 volts times square root of 2 relative to our center point. But while this is held at that 400 volts times square root of 2, this plate of the rectifier is at effectively negative 400 volts relative to the center tap because the phase relative to center is opposite, right? Our center tap sets to ground, sets our 0, so this is at plus 400 volts, this would be at negative 400 volts. So the plate would be at negative 400 volts times square root of 2, while the capacitor is at positive 400 volts square root of 2. So the inverse voltage between the output at the cathode and the plate that's swinging in the opposite direction that's not conducting current, hence it's called reverse or peak inverse voltage, is at 800 volts times square root of 2 across the tube. That is very typical. That's a pretty high voltage, but that's what these rectifiers should be able to handle. In 2845, we can't use this arrangement because we need an output voltage that's higher than, say, 400 volts times square root of 2. We're looking at 1,000 plus volts. So one of the ways to reduce the inverse voltage across the rectifier is go to a bridge rectifier arrangement where you don't have a center tap. So because we don't have a center tap, the voltage, the peak inverse voltage that any tube sees is the voltage of this winding. If we wanted to, say, get 1,000 volts and use the full wave arrangement, we'd have to do 1,000, 0, negative 1,000, and therefore we'd have 2,000 times square root of 2 across the tube. That's way too high. If we use this bridge rectifier arrangement, we can do 1,000 volt winding and get 1,000 volts output with only 1,000 volts square root of 2 across the tubes in their peak inverse voltage condition. That's pretty high for a tube rectifier. GZ34 is what we use. That's kind of on the edge of the data sheet for peak inverse voltage. But a good strong tube shouldn't be an issue there. However, that's not necessarily great design stressing them that way. So one way we alleviate that issue is actually put series diodes in series with the plates. And in fact, we even have balancing resistors. So resistors across the tube and then a resistor across the diode to balance the leakage current in the reverse direction when the rectifier is turned off, to ensure that the voltage dropped across each device is actually half of what it would normally be. So we're dividing the peak inverse voltage in this arrangement. Half of it goes across the tube that's non-conducting and half across the diode, simultaneously while this other path is delivering current to the load. So, right, they deliver current in alternating pulses relative to the phase of the winding. So if this phase is not delivering current and this phase is, it's blocking, it's reverse blocking the voltage that's maintained on this capacitor during the phase where it's off. So anyway, peak inverse voltage is not the issue, especially since we have these balancing or these series diodes to balance the reverse voltage. However, if you read online, a lot of people say, oh, you need these will save rectifier tubes and all that. Yeah, and they're a great idea, and they probably do help with, rectifier lifetime and helps reduce the voltage drop. But the real problem that these don't save you from, and the reason I think we started having tube rectifier arcs, is the startup condition. So normally, and like what we do with 2845 and any of our products that we build, we test them out, we bring them up slowly on a variac first, let everything stabilize and make sure everything's happy before we hard switch, the power onto the amp when it's plugged into the wall as a, user would. 2845 with all of these rectifiers is fine in that condition. And so we can bring it up to the full operating voltage with the peak inverse voltage and never have an issue. So it's clear that peak inverse voltage is not the issue with this arcing. It's something else is going on. So after a little bit of thinking and figuring out that the arc when you do a hard power on, what it turns out is a batch of bad rectifiers we got arc on power on when the vacuum tubes are just starting to conduct. So if you turn this on, the filament hasn't warmed up yet. And because the filament's not warm, the tube can't conduct current as the AC is alternating. Neither tube can. So as this AC is alternating, our capacitor's discharged, or our filter and our power supply or load is discharged. The voltage from the plate to the cathode is actually the full voltage of our AC winding. Once the tube conducts and warms up, that voltage collapses and keeps dropping as this capacitor charges up and comes up to our B plus voltage. The voltage across the rectifier, the forward voltage, just drops until you get, a very low voltage. And for like a 5A or 4 GZ34, it's like maybe 20 volts at, the operating currents we're at. So at startup, the forward voltage drop across the vacuum tube is really high, and then it starts collapsing towards zero as the tube warms up and charges up the capacitor. That's when the arc happens. It has nothing to do with the reverse or peak inverse voltage you often see talked about online or in data sheets. It has nothing to do with them blocking reverse voltage, because again, we're balancing it, and we're still within spec even if we didn't have a diode, although it would be marginal. You definitely want the diode in there. But anyway, that's not the issue. It's the forward blocking that the tube has to do when it's cold as the filament warms up. And so we saw an entire batch of rectifier tubes basically failing in 2845, and we basically needed a way to pre-screen them. An arcing rectifier is really hard on the power supply components, the power transformer, and all that stuff. Now, luckily, in 2845, we've got protection provisions which actually worked and saved the amplifier from any damage. There's some internal fusing inside 2845 that's designed to save the amplifier should an issue like this occur. And so, luckily, or I guess maybe not luckily, but in finding all these arcing rectifier tubes, we happen to test those protection mechanisms in 2845, and everything works and is happy. We didn't damage anything of the amplifier, which is great. But we still want to avoid this if possible, and we want to make sure we don't, put rectifier tubes that could arc or have a potential to arc, especially stuff that we send to our customers. That's just not good practice. So we had to build this, our rectifier tester. And from that startup condition, what we learned is it was very clear that these tube manufacturers really just kind of push whatever they make out into the market. So, we buy these tubes from maybe the manufacturer directly or distributor, wherever we get them from. It was very clear they haven't been tested because we had a batch of these tube rectifiers that were failing at half their rated voltage. So this tester can test either 510 or 1020 volt AC across a winding, kind of as drawn here in the bottom. So in that 510 volt case, the peak inverse voltage is pretty darn low, especially since in this tester we've got it implemented as drawn with diodes. So our peak inverse voltage is quite low. So that's clearly not the issue, but they're still arcing on startup. And so what I think is going on here is poor quality control with spacing and or like uniform coating of the cathode oxide that produces all the electrons of the filament. So on startup, you apply voltage to the filament has to warm up, and then you get a cloud of electrons which then move to the plate and give you your current flow. If the plate becomes negative relative to the cathode, you don't get any current flow. You get a diode effect, and that's how a tube rectifier works. That's how we block reverse current and pass forward current. But on startup, if the filament is coming up and the cathode's, that I've drawn as a square outside the filament is starting to warm up, and maybe it's warming up non-uniformly, or the gap between the plate and the cathode is a little closer in an area, you can get a hot spot where you get, kind of all your current density in one kind of area of the cathode, because it's not uniformly heated and it doesn't have a uniform, distribution of current density because you don't have free electrons everywhere around the cathode. So with this hot spot, you can get really high current densities in a small area that has to flow from the cathode to the plate. And if there's any residual gas in the tube, this really high current density will yield ionization of any of the residual gases in the tube, and an arc can be sustained because now you've got all these free gas ions floating in what should be a perfect vacuum. And I think that's what's happening here. So on startup, when the filament is just warming up and the plate to cathode voltage is the full voltage of the winding, essentially, because our capacitor is discharged, we can get an arc. And data sheets talk about this in tube rectifiers. That's why, for those who are familiar, tube rectifiers have a maximum rated capacitance they can work into and a minimum AC resistance to limit the potential current flow for this startup condition. And just to keep the ripple in steady state, the current ripple of the rectifier in check in steady state as well. So we're maintaining, or we're adhering to all those guidelines by a pretty large margin in 2845. But like I said, we got a batch of bad tubes that are exhibiting this arcing. So anyway, back to this tester, what we can do is we can plug in the tube, flip on the power, and flip them on as it would be an amp, and check if they're going to arc at this lower voltage. If they pass this lower voltage, we can then run up to this higher voltage and see if they'll pass there before we put them in 2845. The other thing this checks for is the actual output voltage for either of those two settings. So we can also just make sure the rectifiers are healthy, and when they work into the load dummy load and the dummy power supply we built into this box, we can see if and make sure they're matched in getting the same power supply output voltage. So it's really handy for that. But I think, as I mentioned, it was just clear that with this batch of bad tubes, they weren't tested from the manufacturer, because even at this lower voltage, which is way within datasheet operating conditions, we're getting arcs. Some so strong that they're blowing the fuse. Others the tube would arc and actually self-clear. So you'd get an arc on startup, and then you'd never see it again. You could keep turning the power supply on and off, doing this warm-up condition, and it would never arc again. So that's kind of a pretty clear statement that the manufacturers aren't testing these tubes in any sort of real-world condition like a power supply. Because if they had, it would have arced at the factory, and I would never have seen this. But no, we're seeing them here. So just another kind of delay for, Project 2845 goes into things like this. We have to build our own test equipment to test every piece that comes in, because we can't be relying on manufacturers, unfortunately. And it's a shame, because it makes our products even more expensive, because we have to eat the cost in a lot of cases. So, for example, we had a batch of the batch of rectifiers that had an issue were sitting new on the shelf for a year, but because they were sitting new on the shelf for a year, and then we started testing them and found these issues, the manufacturer wouldn't take them back because they were outside of the return time window. So we just have to eat that cost. So part of building this is hopefully we will, as soon as we get a batch of rectifiers in, we're going to test them on this. And if there's an issue here, we can immediately go and try to talk with the distributor or manufacturer and get replacements or our money back. But it's just a shame that you can't trust any of the components, even well within their recommended operating ranges. They're just not tested. Vacuum tubes especially, like I said, in the last couple years I've seen throughout the 2845 project and with our other products, just can't really be fully trusted. You have to really test them exactly as you're going to use them in the product. For all the nuances I discussed here, you really have to test them exactly as they're going to be used in the product to ensure that they work. And they have to work. We expect our customers to be happy with our products, and our products aren't cheap. So with that comes things like this. So anyway, as maybe a fun little test really quick, I've got this plugged in to our Variac. We set the Variac at a fixed, turn it on here, 110 volts. So 110 volts produces the AC voltage I listed here. It's a little bit off because the transformers in here have a little bit of overshoot, or the regulation is bad, where if you put 120 into this transformer, we actually get more voltage than we want. So I just run it into the Variac at 110 volts, set mains to 110. So anyway, our mains is on. We've got a tube. I've actually not tested this one yet. In the rectifier tester, I'll hit power and we can see what happens, and maybe if it arcs, you'll hear it too. So it's on, it's warming up. There you go. Voltage came up. And it's running. So no issues with this one. So that would be a candidate to potentially move on to the 1020 volts. I'm not going to do that actually, because this is from the batch that I've had issues with. So I know at 1020 volts it's going to arc and take out all those fuses and kind of be a mess. I was hoping that maybe this one would arc at that lower voltage like some of the other ones, but I guess it didn't. But anyway, that's what you get for trying stuff live. Anyway, I hope you enjoyed this little aside kind of into some of the behind the scenes and some of the extra work we have to do to build high quality tube amplifiers. It's a lot of work. It's a labor of love for sure, especially to deliver a quality product that's going to be consistent and reliable for our customers. And this is the stuff you have to be willing to do and go through. And this stuff's not cheap. These transformers, all this stuff, it's off the shelf. But to build something like this, I mean, I don't know what we have into this tester, but it's a shocking amount of dollars. So it's definitely a shame that we have to do this and actually test components even at like recommended operating conditions that data sheets show. But that's just what we have to do. Anyway, hope you enjoyed this one and take care.